Module 2, Limits and Rates of Change, Part 3. Our engaging context for this section is the Cocoa Crater Trail near Honolulu, Hawaii. My family and I traveled to Hawaii and hiked that trail in March of 2025, and I recorded my statistics of my hiking on that trail. You can see I've recorded my distance, my elapsed time, my elevation, my heart rate as we hiked that trail. So we're going to look at my hike and my statistics as an average rate of change. Prior knowledge that will be helpful as we go through this process is to remember the term covariation refers to how two quantities change in relation to each other. A common approach to quantifying covariation is to compare the change in one quantity, delta y, to the change in the other quantity, delta x. This is customarily the vertical change compared to the horizontal change. Covariation may be represented graphically by using calculus triangles. A calculus triangle has base of the length delta x, that horizontal change, and height of length delta y, that's the vertical change. The hypotenuse of the triangle is the line segment connecting the 2 points used to calculate delta x and delta y. Learning task number 1. What was my average pace in minutes per mile over the first tenth of a mile, between 4/10 and 5/10 of a mile, between 1 mile and 1.1 miles, between 1.5 miles and 1.6 miles, between 2.2 miles and 2.3 miles, over the entire 2.4 mile hike? Explain the practical meaning of these average paces. That is, not only do we want to be able to do the calculation, we want to be able to make sense of what that calculation means. Pause the video and work the learning task. What was my average pace in minutes per mile over that first tenth of a mile? We know that that first tenth of a mile took us 2.57 minutes. If my pace were to remain constant for each additional tenth of a mile, it would take me 2.57 minutes for each tenth of a mile. It will take 10 of those for me to get to 1 mile. So the amount of time it will take will be 10 times those 2.57 minute intervals. In other words, the total time to go 1 mile would be 25.7 minutes. Again, that assumes that my pace were to remain constant for that next 9/10 of a mile to get to a full mile. What was my average pace in minutes per mile between 4 and 5/10 of a mile? Well, we know that that distance took me 2.8 minutes. And once again, if my pace were to remain constant for each additional tenth of a mile, it would take me 2.82 minutes for each tenth of a mile. Because it will take 10 tenths of a mile to get to a full mile, the amount of time it will take me is 10 of those 2.8 minute intervals, or in other words, the total time to go 1 mile would be 28.2 minutes. We continue with this reasoning for the remaining problems. And we get 27.3 minutes per mile between 1 and 1/10 of a mile. Between 1.5 miles and 1.6 miles, we get 24.5 minutes per mile. Between 2.2 and 2.3 miles, we get 19 minutes per mile. And over the entire 2.4 mile hike, we get that my average pace was 26.1 minutes per mile. What do all these values mean? It means if my pace were to remain constant, which we know it didn't, but if it were to have remained constant, this is how many minutes it would take me to hike 1 mile. Learning task number 2, graph the elapsed time as a function of distance over the interval 0 to 0.5. Now, when we see this language, elapsed time as a function of distance, whatever follows that phrase as a function of is the independent variable or the input. In this case, distance is the input and elapsed time is the output. That interval then is a distance interval going from 0.0 miles to 0.5 miles. Our task is to use calculus triangles to represent the average pace over each tenth of a mile interval, and finally determine the interval where I was hiking the fastest. Pause the video and work the learning task. Here I have graphed my distance and my elapsed time. Notice distance in miles is on the horizontal axis, elapsed time is on the vertical axis. I plotted the corresponding points and then connected those points with straight lines. Notice that the horizontal change is consistently 1/10 of a mile, but those vertical changes, or the elapsed time, varies. Over the first 1/10 of a mile, it took me 2.57 minutes. That next 1/10 of a mile, between 1/10 and 2/10, took me 2.68 minutes. Between 3/10 and 4/10 of a mile, it only took me 2 minutes to cover that 1/10 of a mile. And because that was the smallest amount of time, or the shortest amount of time, that is when I was hiking the fastest. Learning reflection. In your notes for your future forgetful self, describe the steps for calculating an average rate of change. Explain the conceptual meaning of an average rate of change. Explain the relationship between average rate of change in a function over an interval and the calculus triangles over the same interval, and record any additional insights. Pause the video and record your learning reflections. We'll continue our conversation, but we want to build on some prior knowledge. Recall that the grade of a road or a trail is the slope represented as a percentage. For example, a trail with an upward grade of 10% rises 10 feet vertically for each 100 feet of horizontal distance. Similarly, a trail with a downgrade of 10% falls 10 feet vertically for each 100 feet of horizontal distance. Also, remember there are 5,280 feet in a mile. For learning task 3, I'd like you to determine my average grade over these intervals. Over the first 1/10 of a mile, between 4/10 and 5/10 of a mile, between 1 mile and 1.1 miles, between 1.5 miles and 1.6 miles, between 2 and 2/10 of a mile up to 2.3 miles, and over the entire 2.4 mile hike. And then explain the practical meaning of these average grades. Pause the video and work the learning task. So what was the average grade over that first 1/10 of a mile? I can calculate my vertical change, which was 21 feet vertically, over that first 1/10 of a mile. Well, I know a 1/10 of a mile is equivalent to 528 feet. Recall, there's 5,280 feet in a mile, so a 1/10 of that is 528. Well, when I'm talking about a unit rate, I want to look at this in terms of per 100 feet horizontally. And so if I do divide the 21 by the 528 and then multiply by 100, I get the 3.98 feet vertically per 100 feet of horizontal change. Because grade is displayed as a percentage, we write the vertical change per 100 feet of horizontal change as a percent. That is, the grade is 3.98%, or about 4%. What was the average grade between 4/10 of a mile and 5/10 of a mile? Again, we calculate that vertical change, which was 137 feet, for over that 1/10 of a mile, which is the same as 528 feet. We convert that to a unit rate, if you will. We get that 137 over 528 is equivalent to 25.9 over 100. So because grade is displayed as a percentage, we write the vertical change per 100 feet of horizontal change as a percent. That is, the grade is 25.9%, so much steeper than what we saw initially. And we can repeat these calculations for the indicated segments of my hike. Now notice on these calculations, the next 3 values are all negative. What does that mean? Well, it means that I'm having a vertical drop rather than a vertical gain. So if the grade were to remain constant, this is how many vertical feet I would drop, if negative, right, over the next 100 horizontal feet. So 10.4 foot vertical drop per 100 horizontal feet, or 11.9 foot vertical drop per 100 horizontal feet, and so on. When we get to the final calculation over the entire 2.4 mile hike, what was my average change in my vertical position? It turns out to be 0.0% because I ended up where I started. And so the net change there vertically was 0. And so when I do that calculation, I get 0% grade on average. Learning task number 4. Convert the distance from miles to feet for the interval 0.3 of a mile to 0.9 of a mile. For example, 0.3 of a mile is 1,584 feet, since there are 5,280 feet in a mile, and 0.3 of that quantity is 1,584. Then graph elevation E as a function of distance in feet, d, over that interval from 1,584 feet to 4,752 feet. Use calculus triangles to represent the average grade over each 528-foot interval, and then determine the interval where the trail was the steepest and explain how you know. Pause the video and work the learning task. So I've graphed my data. I've got the distance in feet horizontally, and I've got my elevation in feet vertically. And I plotted those points and drew line segments connecting each of those points. We can see that the horizontal change is consistent. It's constant, 528 feet each time. And then we've got the corresponding vertical changes. The greatest vertical change occurs between 3,696 feet and 4,224 feet. That's where the vertical change was 206. I can do the calculation, 206 divided by that 528 feet of horizontal change, and I get 39%. That's a very steep grade, and that part of the hike was pretty tough. Learning reflection. In your notes for your future forgetful self, explain how to keep track of units when calculating average rates of change. Identify limitations of using an average rate of change to describe the relationship between two covariational quantities, and record any additional insights. Pause the video and record your learning reflection. We are now going to continue our discussion by investigating instantaneous rates of change. My elevation E in feet as a function of the distance I had hiked d in miles over the first mile of the hike may be modeled by this function. E is equal to negative 1,592 d cubed plus 3,259 d squared minus 615 d plus 143. Again, this is a model for the distance my elevation is a function of the distance I had hiked. Learning task 6. Use the model to calculate the average rate of change for the following distance intervals, from 0.5 to 0.6 of a mile, from 0.6 to 0.7 of a mile. Explain the practical meaning of these average rates of change. And finally, determine at what rate was my elevation changing at 0.6 of a mile and interpret the practical meaning of the result. So I start off with the function equation I'm given, and I evaluate that function at the following values of d, at 0.5 of a mile, at 0.6 of a mile, and at 0.7 of a mile. I get the corresponding elevations of 451.3 feet, 603.4 feet, and 763.4 feet. And then I calculate the average rates of change over those tenth of a mile interval. So on the first one, we have a change of 1,521 feet per mile. For the second interval, we have a vertical change of 1,600 feet per mile. So between 0.5 of a mile and 0.6 of a mile, my elevation was increasing at an average rate of 1,521 feet per mile. That is, if my elevation changed at a constant rate, I would gain 1,521 feet over the next mile. That is, from a half a mile all the way out to 1.5 miles. Similarly, between 0.6 and 0.7 of a mile, the average rate increased to 1,600 feet per mile. That is, if my elevation changed at a constant rate, I would gain 1,600 feet over the next mile, from the 0.6 of a mile to 1.6. To estimate the rate of change at 0.6 of a mile, we calculate the average rate of change over a small distance interval, close to 0.6 of a mile. I chose to just go from 59 hundredths of a mile up to 0.6 of a mile, and then also look at 61 hundredths of a mile and the 0.6 of a mile. I do the calculation there, and both calculations turned out to be 1,580 feet per mile. So doing two different estimates got the same value. I'm pretty confident that's how my elevation was changing at that point in time. So based on these results, we estimate that at 0.6 of a mile, my elevation was increasing at a rate of 1,580 feet per mile. That is, if my elevation changed at a constant rate, I would climb 1,580 feet over the next mile. As we continue this discussion of average rates of change, it's helpful to be able to talk about an instantaneous rate of change. In the prior example, we estimated an instantaneous rate of change by using a small delta, if you will. Let's formalize that language. The instantaneous rate of change of a function f at x equal a is given by f prime of a. That's the notation we use to represent instantaneous rate of change. Equals the limit as delta x goes to 0. Remember, delta x is that horizontal change, and we're letting that go to 0, as close to 0 as we want, of the quantity f of a plus delta x minus f of a. That's our vertical change, divided by delta x, once again, our horizontal change. So basically, we've got our average rate of change formula, if you will, and we throw a limit on the front of it to say that we want that horizontal change, if you will, to get as close to 0 as we want. And that will give us, in fact, an instantaneous rate of change rather than an average rate of change. That's the rate of change at a single point in time or a single instant, depending what our variables are. Alternatively, this could be written as f prime of a equals the limit as delta x approaches 0 of 1 over delta x times the quantity f of a plus delta x minus f of a. This form of writing it helps us visualize that we're actually scaling that vertical change such that it'll be the vertical change that corresponds with a 1 unit change in the horizontal variable, whatever that independent variable is. But both forms are useful. Learning reflection. In your notes to your future forgetful self, explain the meaning of each component of the instantaneous rate of change formula for a function. The instantaneous rate of change in a function f at x equal a is given by f prime of a equals the limit as delta x goes to 0 of f of a plus delta x minus f of a all over delta x. So again, in your notes, record what does f prime of a mean? Remember, that represents the instantaneous rate of change in the function at x equal a. What does this limit as delta x approaches 0 mean? What does the f of a plus delta x mean? What does f of a mean? What does delta x mean? What does that overall ratio mean? And so I want you to make sense of each component. If you have a solid understanding of this, everything we do in this class will be much easier for you. And if you don't, everything will be hard. So take some time, make sure you learn this.